name is Elijah Martinez, and this is Lab 3, brought to you by Group 1 at 8:30. In this lab, we will be investigating how forces produce acceleration. Again, we will be using an air track connected to a string with a weight attached to it, drastically reducing friction. This will allow us to observe the motion that closely resembles ideal conditions that we're looking for. This is described to us in our physics lecture, where the net force acting on an object leads to a predictable acceleration, especially Newton's second law, where its acceleration is directly proportional to the net force applied on it and inversely proportional to its mass. Experiments using air tracks are widely used in physics because it isolates this relationship so clearly. With friction minimized, the motion sensor can then record accurate position versus time data. This lets us see how a constant force from a hanging object, or mass in this instance, produces a measurable, nearly constant acceleration. This phenomenon isn't just theoretical. It's the same principle behind real-world systems such as elevators, roller coasters, and even spacecrafts. Engineers rely on these force and acceleration relationships to design machines that move safely and predictably. By studying this simplified version in lab, we can then get a clearer understanding of how forces shape motion in everyday technology. I will now be handing it over to my teammate Daniela, where she will then explain all the materials that we use in this lab and how we use these materials to produce our calculations.
Hi, my name is Daniela, and now I will explain the materials we use for the lab number 3. So for this experiment, we use several materials to analyze the acceleration of the system and compare our experimental results with the theoretical values from Newton's second law. So first, we use an air track and a glider. The air track was connected to an air pump, which reduced friction by creating a thin layer of air under the glider. This allowed the glider to move more smoothly and help us get more accurate results. We also used a pulley system attached to the end of the track along with a hanging mass. The hanging mass created the net force that caused the glider to accelerate. So by adjusting the mass, we were able to observe how changing the force affected the acceleration. In addition, we used extra masses to change the total mass of the system when needed. It was important to measure the masses carefully because they were used in our theoretical calculations, so we measure all the masses using a triple beam balance to ensure accurate measurements. So to collect our data, we used a motion sensor connected to the Capstan software, and the sensor allowed us to measure position, velocity, and acceleration in real time and generated graphs to analysis. And finally, we use a computer to run the Capstan program and analyze the data collected during the experiment. So all of these materials were essential for reducing friction, applying force, and accurately measuring acceleration in our system. So now I'll pass it to my teammate to explain the procedure.
Good evening, my name is David Maldonado. I'm going to be discussing the procedure for our lab number 3. In this procedure, we describe acceleration using the force or the acceleration, mass of weight, mass of cart, and the gravity constant, described as A equals mw times g over mw times mc. For gravity, if it is going towards the sensor, that would be negative 9.8, which is the constant. And if it's going away from the sensor, that would be 9.8 m over s to the second power. For acceleration, we use the formula A equals final velocity minus initial velocity over final time minus initial time. This objective, we'll be using the capstone graphic presentation and data gathering. We're going to be using the acceleration to meet this goal. First things we discuss is the friction and resistance are negligibles in our experiment, and after that we have the equipment setup. Our equipment setup is due to the hanging weight, the pulley, and the mast of the cart described here. For the hanging mast, this would be our MW force constant, and this is our MC. The pulley will be faced down like this. If the C is going towards the center, once again, it's gonna be the negative 9.8, and if it's going away from the center, it will be negative 9 point, or it will be positive 9.8. My apologies. For our first one, we'll be setting up our data processing. We'll be discussing position 1, time 1, and the position change. We'll be doing this for 4 separate points actually, so we can get our variables for our initial velocity and our final velocity. After that, we'll be making our table for acceleration 1. Step 3, where we finally will be adding a graph and capstone, and we'll be using velocity as our measurement. We'll be just selecting our initial and final velocity points to compute what we will call acceleration. In table 3, we'll be annotating our velocity 1 and annotating 1 to get acceleration 2. From here, we'll be doing the exact same thing. We'll only be changing acceleration as our measurement from velocity, and we'll be scaling our information, highlighting the icon, and moving the scalar shadow to select the points that belong to the first time interval. After that, we'll be comparing our percent error, which is the formula percent error equals theoretical value minus experimental value over theoretical value times 100 to get our percentage. This will give us our percent errors for acceleration 1, acceleration 2, and acceleration 3. For step 6, we'll be answering these 5 questions. Should the percent errors be similar or not? Where did the error come from? Can or should this error be precisely 0? Set with your team members the threshold of this value to consider a good, regular, and bad experiment of this time. If you have to calculate acceleration again, which method will you choose? And finally, we will write a lab report. This is all to show acceleration through a pulley system.
This is Alejandro, and I will be doing the data and data analysis for Lab 3. We were tasked to find the acceleration 1, acceleration 2, acceleration 3, theoretical acceleration, and the percent error of each of our accelerations. For the first step of our lab, we made sure to weigh out the glide and to weigh out the mass of the hanging objects. For the mass of the glide, we got 0.1966 kilograms. And for the mass of the hanging objects, we combined the 5 grams of the hanging object plus the 10-gram weight we placed on it to get 15 grams. And then we converted it to kilograms, which gave us a total of 0.015 kilograms. Using those two numbers, we plugged it into the theoretical acceleration formula. We plugged in 0.015 kilograms divided by 0.1966 kilograms plus 0.015 kilograms times 9.81. This gave us a total theoretical acceleration of negative 0.694707 meters per second squared. For the next part, we turned on the glide in order to get a graph on the capstone program, which would give us our position times time graph, our velocity times time graph, and an acceleration times time graph, which would select 4 different points in order to get each of our data points. For position 1, the point was set at 0.66 meters at 2.4 seconds. And for position 2, it was set at 0.65 meters at 2.463 seconds. Using those numbers, we got a position change of negative 0.01 meters and a time change of 0.063 seconds. For position 3, we had it set at 0.52 meters at 2.9 seconds. And for position 4, we had it set at 0.5 meters at 2.950 seconds. For that, we got a position change of negative 0.04 meters and a time change of 0.05 seconds. For our initial velocity, we plugged in negative 0.01 meters divided by 0.063 seconds, which gave us a total initial velocity of negative 0.1587 meters per second. For the final velocity, we plugged in negative 0.02 meters divided by 0.05 seconds, which gave us a total final velocity of negative 0.4 meters per second. For step 2 of the lab, we used our acceleration formula, plugging in the numbers we gathered, negative 0.4 meters per second minus negative 0.1587 meters per second divided by 2.950 seconds minus 2.4 seconds, which gave us a total acceleration 1 of negative 0.43 meters per second squared. For step 3 of the lab, we used the same points for step 1 except on the velocity graph. For velocity 1, we got negative 0.18 meters per second and a time 1 of 2.5 seconds and a velocity 2 of negative 0.49 meters per second and a time 2 of 2.950 seconds. Using those numbers, we get a velocity change of negative 0.31 meters per second and a time change of 0.45 seconds. Using those numbers, we plug it into our acceleration formula. We get negative 0.49 meters per second minus negative 0.18 meters per second divided by 2.95 seconds minus 2.5 seconds, which gives us a total acceleration 2 of negative 0.68889 meters per second squared. For step 4 of the lab, we use the same points from step 1 and step 3, which would give us a mean value equal to our acceleration 3. Our acceleration 3 is equal to negative 0.67 meters per second squared. For step 5, we gather all our accelerations. Using those accelerations, we plug it into our percent error formula. For acceleration 1, total percent error of 30.906%. For acceleration 2, of 0.837%. For acceleration 3, which gives us a total percent error 3 of 3.556%.
The percent errors could be similar, but if the percent error is off, it could be due to air resistance, residual friction, or even the calibrator itself during our time in the lab. The error percentage was coming from our theoretical acceleration and our theoretical velocity. With 100% perfect measurements, this could technically be 0, but it would be very hard to calculate and would take a lot of time, and it would be time that we did not have during the lab. My team members and I can conclude that this experiment was regular. It could have been better if we hadn't struggled getting our calculations right, but overall, still a good experiment to be a part of. We would most likely stick with the same formula to calculate acceleration. Since we were getting the correct answers, we just had the wrong numbers input into the formula. So we would use the same formula if we had to recalculate acceleration.